Okay, so now if we look at this system, the advantage of taking this system is that now F is applied at this point, and then the direction of F is not changing anymore, which will simplify calculation a lot because F now is constant. So I don't need to get the variation of angle with position and integrate to find the work. So a good selection of my system will simplify things a lot on me. Okay. So when I take this system as a whole, I can say that summation of work between state 1 and state 2 is equal to final kinetic energy, which is half mvb square. And here they gave me, the question is to find F. The only unknown is F, but I have the final velocity of my block, and it's initially starting from rest, so -0. The initial kinetic energy is 0. And VB is given, so I know the final kinetic energy. My only unknown is the force F. So I need to express sum of work. First, for force F, F is applied at this point, okay? And the displacement of my point is equal to what? Here I should pay attention for something, okay? Look, my block is moving upward, a distance SB. But can I say that my hand here that is pulling the cable downward is moving also SB? Look, this is your cable. This is your cable. This is the pulley. And this is your hand. Okay? Your hand was at this level. I will call it, let's say 0.1. Okay? And as your block moved up, what happened? The cable from this side will be shorter, and from the other side will be longer. Okay? And the variation in length of your cable, so if I consider position at position A, this is position A. You have the length of your cable was from this side was LA. Okay? So this is, I will call this is LA, and this part I will call it L1. Okay? Now, at the final position B, the cable part from this side has a length LB. Okay? And from the other side, you will occupy a new position 2, and this is L2. Okay? And here, to relate delta L to delta L, if you want delta small l to delta big L, you can just say I have one cord here. One cord, like we do for pulleys. So we can name this is big L, this is a small l. The total length of the cord is constant. So big L plus small l is constant. Okay? So since the summation is constant, since the summation is constant, then you can say that delta big L, so the variation in length of the cable from the part of the block is equal to minus delta L, which is the variation of length from the side of your hand. Okay, and your hand will pull downward the cable with a distance of delta L. So all you have to do to compute delta L, okay, is to do minus big delta L. So if you want, if we go back to our figure here, it's the length LA minus the length LB, which is different than SA, okay? Which is different, sorry, than SB. So this is equal to LA minus LB. And to get LA and LB, it's really simple from geometry of the figure. And if you look at your figure, okay, they gave you all information needed to calculate your length, because you have at position 1, okay, at position 1, you have this distance is B, okay? B is given to be 0.3 meters. And this distance was 0.4. This distance is 0.4. So you can do, this is a right triangle. You can find the value of this length, okay? By doing radical 0.4 square plus 0.3 square. Now at the final position, okay, you have a new length here because it's shorter. You have L, which is 0.3 minus SB. SB is given to be 0.15. So this distance is 0.4 minus 0.15. It's 0.25. So now you can calculate what is the length of this part. It's radical 0.25 square plus 0.3 square. Okay. And then once you have LA and LB, you can determine the displacement of your hand, delta small l. And you can say that what is the work of F? F is pulling the cable downward and the displacement is downward. So it's a positive work. The work of this force is plus F times delta L. Now, what do we have also? We have the work of the weight and the work of the spring. For the weight, okay, you are moving upward, so it's a negative work, okay? So minus mg times the upward displacement, which is SB. This is the work of the weight. And finally, you need the work of the spring. We know that by definition, how we get the work of the spring, it's half K delta L1 square. They said that the spring is initially unstretched. So delta L1 is equal to 0. Then you cancel out delta L1 minus half K delta L2 square. Okay. So to calculate delta L2, what is delta L2 actually? It's the stretching of the spring. Since your spring was unstretched and you moved upward a distance of SB, and the stretching now is equal to SB. So delta L2 is equal to SB. And then you can replace half K minus half K delta L2 square by minus half K SB square. Okay. And in this equation, your only unknown is the value of F. You have everything except F, so you can calculate F. Any question on this problem? Okay. For example, in this problem, the important thing, the new thing is to pay attention when a force or angle is varying. So here, for example, the direction theta is changing. So theta is function of x. Whenever you have a variation or in magnitude or in angle, you need to do integration to find the work. Okay. So in this problem, we have a block that is starting with a speed v1. So it has an initial speed. So the initial kinetic energy is not zero. And we displace it a certain distance. And we want to determine the final speed. And they said that the rod is not smooth and we have a kinetic friction coefficient mu k. So the first step will be to consider the free body diagram of forces acting on the block. We have the normal reaction. Now, of course, the normal is perpendicular to motion, so it cannot produce any work. We have the weight, but is the weight producing any work here in this problem?
No,
Do we have a work for the weight in this problem?
no, we don't have.
No, we don't have because it's also perpendicular to motion. So no work for N, no work for the weight. But why we need to find N? We are interested in the value of N because the friction, the kinetic friction, which is mu Kn, is function of N. Okay? So we need to determine what is N to use it for the friction. Okay? So the first step will be to say, since I have displacement in X, no displacement in Y, to get N, I use sum of Y equals 0. So I start to say sum of forces along Y equals to 0. Okay? And then I have plus N minus weight, so minus mg minus f sine theta equal to 0. So I get N. And because theta is varying, theta is variable, so N is variable. So my friction also is not constant. My kinetic friction is varying. So also to get the work of my friction, I need to do integration. Okay? So now all I have to do is to replace in the principle of work and energy. The initial kinetic energy is half mv1 square. The forces doing work are first F, but because the direction is variable, to get the work of F, I perform integration from initial position, which is x equals 0 to x1, of F cosine AX dx, minus mu k. Now here, since N also is varying, so I should integrate N dx, and N is equal, as we have developed, is F sine theta plus mg, okay, equal to half mv final square. So I have everything except v final. So just I should pay attention to integrate these functions to get my final velocity. Okay, so the main idea of this problem is to pay attention whenever we have a force varying or in magnitude or in the angle or in direction, we need to perform integration to calculate the work of the force. Any question on this problem?
Yes, can you
Yeah.
please repeat how we came up with the work of the friction, please?
Okay. By definition, how you calculate the work of a force? The work of a force is integral F times cosine. I will use instead of theta alpha here because theta is already present. I will say N cosine alpha dx, okay? But mu k N, sorry. But what is the angle between your friction, the friction and motion, and the direction of motion? This is the direction of motion, okay? It's in positive x, and the friction is pointing in negative direction. So they are opposite. The normal, the friction and the displacement are opposite. So what is alpha? Alpha is 180 degrees, okay? That's why the work of the friction is negative, and the work of friction force is equal to minus integral mu kn dx. Okay? Now, what is your normal?
Okay, then.
You
E sigma.
calculate your normal from this equation. No, your normal is mg plus f sine theta. So okay.
Yes.
Okay.
Thank you.
Okay. So the work of friction, you can take mu k outside because it's a constant, is minus mu k times you integrate from the initial to the final position from 0 to x1, and you replace the friction by mg plus f sine ax, sine theta, and theta is ax. So plus f sine ax times dx, and you integrate, okay?
Yeah, thank you.
Okay, other question on this? هلا this problem For this one, I think we have solved something similar before. We discussed it last time together, if you remember. Okay. For this one, the flying car is a ride at an amusement park, which consists of a car having wheels that roll along a track mounted inside a rotating drum. By design, the car cannot fall off the track. However, motion of the car is developed by applying the car's brake, thereby gripping the car to the track and allowing it to move with a constant speed, VT. If the rider applies the brake when going from B to A and then releases it at the top of the drum so that the car coasts freely down along the track to theta equal pi, determine the speed of the car at B and the normal reaction which the drum exerts on the car at B. Neglect friction during the motion from A to B, and the rider and car have a total mass m, and the center of mass of the car and rider moves along a circular path having a radius r. Okay, great. So here what they are telling you, when moving upward, we are applying a force in a way to reach A with a velocity v. So we know the velocity at the top, okay? The velocity at the top is known. Let's say we have v top, okay? It's in the opposite direction. We are moving counterclockwise. So v top is horizontal at A, okay? Tangent to the path. And now we move from A to B, we move under the effect of just of gravity because they said that we are not applying any engine force from A to B. So we are moving downward under the effect of gravity. So the only force doing work is the weight. Because if we consider forces, we have the weight and we have the normal, since no engine force is applied. Okay? So since the normal is always at any position, the normal will be perpendicular to the tangent line. So it is perpendicular to motion, then the work of n is 0. We only have the work of the weight. Okay? And to get the work of the weight, we have two methods. Or we apply principle of work and energy, or we apply conservation of mechanical energy. Both will give us exactly the same result. Let us try to do this. If you want to apply work and energy principle, what do you say? You say the initial kinetic energy is half mass times V top square. Plus, we need to consider the work of weight. The work of weight, okay, between A and B is equal to what? I use the formula. Work of weight is minus mg delta y. But what is delta y here? I put minus mg delta y if I consider y axis to be positive upward. Delta y is the difference between YA and YB. And delta y here is y final minus y initial. It's YB minus YA. And since I consider y to be positive up and my car is moving down, so YB minus YA is negative. Okay? For example, if you consider the origin to be here, YB is 0, while YA is 2 times the radius. Okay? So delta y will be equal to minus 2r. And since I already have a minus will give me plus. So the work of weight is plus mg times 2r. Okay? Equals to the final kinetic energy. The final kinetic energy is half mvb squared. The only unknown in this equation is the final velocity. I can solve for the final velocity. Now, if I want to use the principle of conservation of mechanical energy, what can I say? I can say the gravitational potential energy at point A, V gravitational at A, plus the kinetic energy at A, which is half mv top square, equals to gravitational potential energy at B plus half m VB square. And I need to consider a datum, okay? I can take the reference wherever I want. If you take this as this point B as your reference, and the datum is passing by B, then V gravitational B is 0, and V gravitational A is plus mg times, because you are above the datum, it's plus mg times this distance, which is 2r. So V gravitational will be plus 2 mgr. So you get exactly the same equation. Let us try to take another datum and we'll see that we'll get exactly the same result. If you consider the datum, for example, at the center, okay, then VA will be positive because I am above the datum. It will be plus mg times r. While for B, you are below the datum. So for B, it will be minus mg times r. Okay. And in both cases, now if you replace, if you take this term to the other side, you will get again plus 2 mgr. So it doesn't matter where you take your reference because delta V will remain the same. So of course, nothing will change in the value of V final. Okay. Now, they also asked us to find the normal reaction at point B. Okay. How can we calculate the normal reaction at B? We need to draw a free body diagram. We consider at the bottom, we have two forces acting on our system. Okay. We have the weight and we have the normal at B. And since we need to get a force, then we need to select a coordinate system. And in general, whenever you have circular motion, the easiest coordinate system to work with is the normal tangential coordinates. So you say ut is along velocity. Its tangent to the path. This is ut. un is perpendicular to ut, pointing towards the center of rotation. So this is un. And since the normal is along un, then I should apply sum Fn equals MAN. And you know that by definition, the normal acceleration is equal to V square over R. Since you are applying at point B, so you need the normal acceleration at B. So it's equal to the mass times VB square, the velocity when we reach point B, over the radius r. We have already calculated VB now. We have the radius, and we project now forces. We have plus n minus weight, so minus mg, equals to mvb square over r. So the normal at the bottom is equal to mg plus, we can take m into factor. So it's m times g plus vb square over r. Okay. Any question on this?
Doctor, in this exercise, we were able to use the work and the energy conservation because we only had to care about the weight.
Yes, because the normal is not doing any work. So whenever you have forces doing work are conservative, you can apply conservation of mechanical energy.
If you are saying anything, we can't hear you.
Okay, I'm saying that you can do this because the normal is not doing any work. So the only force doing work is the weight. Okay? And the weight is a conservative force. So whenever all forces doing work are conservative, you can apply conservation of mechanical energy. Did you hear me, Christopher? 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 Do you hear me now, Christopher?
Yeah, there you know.
Okay. I was saying that, because here the normal is not doing any work. You only care for the weight, and the weight is a conservative force. Because the weight is a conservative force, you can apply conservation of mechanical energy. Okay. So whenever you want to know if you can apply conservation or not,
Yeah.
you should look at forces doing work. If all of the forces doing work are conservative, you can apply conservation of mechanical energy.
Okay.
Okay. Other question?
I do have a question in the yes, in the previous exercise.
Yes. Yes. Tell me. Okay.
Exercise 3, the
Three.
one that we did before.
Okay. Yes.
Yes.
Yes. Tell me.
دكتور هلا ما نحن مثلا روتين كان يجينا اكسرسايز مثلا راد عم يمشي على anything كان يجي اذا مثلا اذا movement horizontal we don't use the weight. Is it
Yes.
applicable in chapter 2
Look, الويت
ولا لا we need to consider weight even
you mean in work and energy? You mean in work and
yes
energy? Look, the
yes
weight will only do a work if you have vertical displacement. If you
true
move in a horizontal plane, the weight will not do any work because delta y is zero.
true so I don't consider it in either way.
You don't consider it. You say the work of the weight is zero because it's perpendicular to motion. But
Yes,
you
okay,
need it just to find the normal.
okay, okay,
Okay,
thank you.
welcome. Other questions?
Yes, doctor, I have a question.
Yes, tell me.
بالريفيو problems chapter 13
Yes,
آخر exercise قبل آخر exercise سوري exercise 12 في
okay.
شيء بالhorizontal ما بعرف شو فينا نفتح exercise please.
Yes, 1 second, was please. Chapter 13.
Yes.
Which problem?
12.
Yes.
أنا عرفت كيف جبنا التاتا والآر بس
Okay.
خلصنا التاتا والآر صار بدنا نعمل ما بعرف إذا بيقولوا له free body diagram.
Yes.
ما عرفت كيف فكرت كرمال جيب هول الفورسات
Okay. Okay. Look.
وكمان في شيء مكتوب horizontal plane
Mm.
كمان قلتي لنا انه هيدي بتعني لنا شيء بس ما عرفت شو بتعني لنا.
Okay. نحن قلنا when the plane is horizontal يعني the weight is vertical is perpendicular to the board يعني the weight if you want to present it okay it's like this. Sorry, 1 second. The weight you can present it like this. You put an X with a circle. It's pointing inward, okay? And you have a normal reaction that will oppose it upward, and they will cancel each other. So these two forces are not in UR theta plane. In UR theta plane, you have the following. I will draw it for you here. This is the particle. The particle is driven by the rod. So the rod will do on it a force perpendicular to the contact line. Okay, this is your rod. So your rod will do on the particle a force perpendicular to contact. This is the contact line, which is the rod line. Okay, so you have the force F. So if you want, I represented for you the slot of the rod. The rod will do on the ball through the slot a force perpendicular to contact. David, do you hear me now?
Hey now.
Do you hear me?
Yes, now I hear you.
Okay.
Yes, yes.
So you have the force that is perpendicular to the particle. Okay.
ما في بس
يلا I
مشينا.
will share. Okay. يلا. Okay. So you have the force of the arm. But also, what do you have? You have this guide here. I will put it in another color. Your particle is also in contact with this guide. With this guide, okay? Now, depending on if you want the ball, I will put it here. The ball can press or on this side or on the other side. You don't know. You need to assume, okay? And you assume here, for example, that the ball is pressing on the upper side, on this one. If the ball is pressing on the upper side,
Okay.
then the force will be downward, like this. In a way that it's perpendicular to what? To the contact line, which is the tangent to the path. And here, you should consider you have a circle, okay? You have a circle here. This is your circle. The normal is perpendicular to the tangent line, so it's along the radius. And the normal should pass by the center of the circle. So your center of your circle, let's say, is here. The normal should point towards, should pass by the center. هلا انت you assumed انه it's downward. You do calculation. If you get positive result, your assumption is right. If you get negative result, your normal is up. Okay? So these are your forces. It's exactly like the problems we did in class, if you remember. N direction is along the radius of the circle, and F is perpendicular to the arm. Now, if you want to put UR U theta, UR is along the rod, okay? Because UR is from the origin. Where is your origin? Your origin is here, okay? So UR is like this. UR is from the particle to the outer side, because it's directed from the origin towards the point. This is UR. So F, if you want, the force of the arm is along U theta. It's perpendicular to UR. And U theta is perpendicular to UR, and we rotate along positive theta direction, which is counterclockwise. So this is U theta. Your only problem is with N, how to find the angle between N and UR. Okay, so in this problem, it's simple because if you want to have a circle, because you have a circle, you know the direction of N. N is passing by this point. So if I want to illustrate it here, this is the direction of UR. Okay. And this is the normal. اوكي
نورمال مش على السنتر.
ايه ما هيدا هو السنتر. صح هو السنتر هو هون. اوكي this is A and this is B. Okay, so this is your normal. Look at the figures. This is your normal. What is the angle between the normal and UR? نحن سميناه phi. دافيد مش أنا وياك امبارح عملنا relation between theta and phi, and you can calculate phi. Okay, so now to project N, it's minus N cosine phi along UR and minus N sine phi along U theta. لأنه UR is up like this و U theta كمان up. يعني normal, according to this assumption, the normal has negative projections on UR and on U theta. يعني I do minus UR cosine phi minus U theta sine minus and along U theta minus N sine phi.
اوكي يعني احنا عنا two forces.
عنا two forces
صح؟
بالhorizontal plane, بس في two forces F و N.
F و
N.
وان لان
بالفيرتيكال دايركشن عندنا الويت
والان.
والان زد، يعني النورمال
ايه
along
صح،
Z.
اوكي.
هلا اذا طلبوا منك find the
اوكي
total normal، بتقول the total normal is decomposed into two components perpendicular to each other. يعني you can compute it in magnitude as radical and z square plus n square.
والان سكوير دي
هي اللي
الان
جبتها
زاد دي
هون، هي
ويت
بقلب يو
اوفر
ار يو
جي.
تيتا بلين، هي هيدي الان this one. اوكي
اوكي هلا نحن بقى هول التو فورسز اللي عنا اياهم، اي وحده يلي جايه على التانجنت بيربنديكولار على التانجنت.
النورمال لانه
النورمال.
انت النورمال جاي من السيركلر جايد. The circular guide is applying a normal force on the particle, so it should be
اوكي.
perpendicular to the tangent line, يعني along the radius. بينما الفورس F is coming from the rod، هيدي الرود هون.
امم
اوكي يعني الفورس F is from the rod والفورس N is from the circular guide.
سيركل.
اوكي
اوكي. 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 طيب. طيب ميرسي.
welcome. اوكي باي.
Doctor,
Yes.
أنا on Tuesday I was absent, so بس I wanted to make sure إنه you didn't assign yet a date for the exam.
No, we didn't.
Okay, طيب. Thank you so much.
Welcome. Bye.
Doctor, do you have any idea إذا رح إنه إذا الفحص ممكن نعمله أونلاين
No, I
ولا؟
don't. هلا I don't know صراحة. نرجع on campus. We need to wait. Okay.
Okay, thank you.
Welcome.